All right, I don't know where everybody is. Just make sure I'm still the only one here. I don't know what's wrong with where we are today. But since nobody's here, I'll go on and get started. I was trying to kill time to wait till folks showed up, but there aren't any folks showing up so far. Just maybe to kill a little more time in case anyone comes in a little later and goes back and listens to this. Just a quick rehash of what's been going on lately. A week ago Monday, late in the evening, my computer started dying. Y'all know that story. I hoped and suspected it was that it could be the adapter that goes from the AC to DC. And I knew my battery was low, so my wife ordered a new adapter and a new battery. But I was afraid it was my connection, not the adapter. But I couldn't do anything about the connection, but we could try the adapter. So anyway, we ordered that. That was Monday a week ago evening. They said 2 to 6 days. We paid extra for more rapid delivery, but even that was going to be 2 to 6 days. So, supposed to then, FedEx said they were going to deliver on Thursday. We were watching for it on Thursday. It never came. Late in the evening, we checked again. It said pending on the truck. So we thought, well, it must be going to come Friday. So we waited till Friday, late in the day. No, it still hadn't come. We checked again. It said they delivered it Thursday morning, which, of course, Thursday evening they had said it was pending and was on the truck somewhere. So we knew that was total make-believe, okay? I'm still the only one in the room, and I don't know what's wrong. I set the invite, I'm pretty sure, so I don't know where folks are. So anyway, FedEx basically either was lying or they had delivered it to the wrong house, okay? One or the other, or they had just lost it or something. I don't know. No, they said they delivered it, so they were either lying or they delivered it to the wrong house. So anyway, that was late Friday before we found that out. Actually, that Friday evening, I saw a FedEx driver. We were expecting another package. He was picking up a package from a neighbor's house after 10 o'clock at night, which was sort of strange. I waved him down and then told him my situation, that we were missing a package for Thursday that that they said they had delivered, and also a Friday package they hadn't delivered either. The Thursday package had not been delivered, and he said, "What's your address?" And I told him, and he looked down beside him and said, "Well, this is yours." And it was the package he had picked up at the neighbor's house, which they had been misdelivered, and I guess he was going to take it back to the his hangar or wherever it was and say it was undeliverable. I don't know what he was going to do with it, but anyway, we got that package, but it wasn't my package. That was fortunately, it was the fish that my wife had ordered, and they had been packed in dry ice. By the time they got here, there was no more dry ice, but they were still solidly frozen, so it hadn't been gone long. So anyway, that was Friday. We also emailed the company, but they weren't in the office until the next Monday morning. By 7:22, they had already shipped another package to us. This time they were coming UPS, thank goodness, okay? So anyway, we, and by the way, in the neighborhood and all over, we were hearing people, FedEx was misdelivering packages, not delivering packages, just a mess, a total mess. So that got us to Monday. Monday, I was teaching my first class, and at 11:20 Monday morning, the internet went out. Okay, so I couldn't be using my regular computer. It wouldn't work. Karen had fixed up a computer we had that had an ancient operating system. She put Windows 10 on it, which is not a very easy thing to navigate. But I was teaching for that, but I didn't have Screencast-O-Matic, and I couldn't right on the screen either. So those two features were gone. So I taught from that until the internet went out. And then I tried teaching from that using her hotspot that she had on her phone. We get such terrible phone service here that she couldn't get a good signal for that, so the hotspot couldn't enhance it much. So that IBM type computer, Windows type computer, just was not working well on that at all. That's why last Tuesday I couldn't even get on until an hour into class. And that's why, or maybe not quite an hour, whenever it was we got in the class. And then we finally had class on Tuesday. Well, then after that we found out that her iPad worked better than that computer did. So I started teaching from the iPad, but that couldn't even have PowerPoint. So I was teaching that, writing on a piece of paper, showing things in the camera, and that was a terrible way to go, but at least we kept going that way. And then after my second class yesterday, I had a 20-minute break before my third class, and I went downstairs to get something to drink and to get a little snack. And right when I got downstairs, she said, "You won't believe this." I said, "What?" She said, "The internet just came on." Jubilation filled the house. We finally had internet again, so I could get off the iPad and get back onto the other computer and at least have PowerPoint. Except we heard something, and she said, "What fell?" I said, "I don't know." She said, "Could it have been a package?" I went to the front room, saw the UPS truck down there, could hardly wait to get the door open, checked. There were 2 boxes. I almost picked them up, and now I remember, no, I'm not supposed to be touching these. So Karen came out, got the packages, cleaned them off, and then opened them up, and sure enough, there was my adapter and my battery. I put them in just in time to start that class yesterday afternoon. So the last 2 classes yesterday and all morning, I've been back on my old computer, back with Screencast-O-Matic, back with PowerPoint, back with writing on the screen. Everything's back like it was when we shut down. So we're back. The only thing that's not back today are the students. And I don't know, I'm still the only one in the room. And I don't know why. I sent out the invite. I don't know. I'm going to pull out of this. I've just been sort of killing time. But let me pull out of this and see if on Blackboard, if the invite got messed up. It stopped the sharing, so you probably see I'm here, but you won't be able to see what I'm sharing. But there's nothing coming up on Blackboard. Let me see if do it again. Well, still nothing on Blackboard. Let me do it again. Maybe I have too many things open, but Blackboard is not opening. Sorry about this, folks. We've had too many problems. This is not time for another one. I'm still the only one in the class. Here comes, my screen sharing is paused. Google Chrome is not responding, it says. That's why Blackboard is not working. Let me get this out of the thing and close this new tab. Close that new tab. Okay. Here it comes finally. Blackboard Learn. This is the new version. Whatever they call it, Ultra. Let me sign in. Okay, for those who may be joining, I don't see anyone yet. Nope, I'm still the only one in. I'm waiting for Blackboard. It's really, really slow, so I'm wondering if Blackboard's having problems. But I would have thought you would have been able to get Zoom whether Blackboard was working well or not. Let's see what's happening. Now it could be that my internet is having problems again, but I've had no indication that's the case. But Blackboard is awfully, awfully slow opening, but it looks like it is opening, finally. And let me get to courses. This is incredibly slow. I guess I have too much open now. Okay, physical science, that's us. And let's see if my announcement is here. There's the announcements. 2 are posted, 3 total. That doesn't make any sense. Ha! It did not post last night, even though I remember posting it. And so maybe someone will sign in now. Okay. Let's see. While I'm here, let me go to okay. I think I will go back to this. All right. Return the meeting. Still the only one here. Yuck. Let me go back to chapter 4. Okay, for some reason it's all black. Ah, there we got it. I don't know where people are though. Ah, we got some people coming in. Jason, good to see you. Can you hear me yet? Okay. Sorry about that. I posted this last night, but evidently Blackboard is still having problems, and even though it said it posted this today, I went to check when no one was here, and it wasn't posted. So, sorry about that. I did it last night. I can't hear you. Say a little louder.
I was talking to somebody else.
Oh, okay. Okay. So, anyway, Jason's here. So we got at least one person. Hopefully we'll have some more showing up. Oh, there's Perrin. Okay. Gunner's here. All right. Any others? All right. If y'all see anyone show up, please let me know so I can get them added. Because when I've got all these things open, I don't get sometimes don't get the indicators when people show up. All right. I had been talking for a while waiting for someone to show up. When they didn't, I went to check. Blackboard would hardly open. When I finally got it open, I found out it must be having problems because last night I posted this. I remember posting it, and today it said it wasn't posted. It was out there, but it said it wasn't posted. So I posted again, and evidently that's when y'all saw it to pick up on it. So sorry about that. Seems like some new people have shown up, so let's see who else is here. Chad is here. Good deal. Okay, who is that? Tarsha's here. Okay, now I see you. Okay. I was just saying, evidently, Blackboard is still having issues because I posted this announcement last night. I remember checking and making sure it was posted, and then this morning it said it wasn't posted. But, I mean, this afternoon it said it wasn't, because I was here talking to myself for a while, waiting for someone to show up. And I said, I can't believe they're this late, so I went to check, and sure enough, it had not posted. So I added it, posted again. Someone else has just come in. I can't see who that is. Oh, Samuel. Sam's here. All right. There he is. Okay, let's see how many we've got now. 6, 1, 2, 3, 4, 5, 6. That's right. If y'all see anyone else pop up and they don't say something for me to hear, please let me know. Oh, now we got another one. Let's see this. That's Josh. Hello. Josh is here. Okay. So we got 7. 1, 2, 3, 4, 5, 6, 7. Okay. All right, well, let me know if you see anyone else pop up. Sorry about the delay. I posted this last night, and this afternoon when no one showed up, I went back to check on Blackboard to see what the problem was. Blackboard would hardly open. I mean, I waited, I don't know how long for it to open and then move from one screen to the next screen. I mean, it was like molasses. Someone else has just added. Anyone know who that is? Zane is here. Okay. So we're up to 8, I think. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Yeah, I make 9. So it says 9 participants, but I'm one of them. So if you see anyone else pop up, let me know. Well, I'll leave it up here for a minute while I explain what is happening, or has happened anyway. I was just going through this trying to kill time waiting for people to show up. Finally they didn't, so I quit and went and checked. Anyone who may have been missing some of this long, sad saga, let me review it with you. Monday a week ago in the evening, I was trying to I'd been checking emails and printing labs and tests and other things that had come in, and my computer just started going out on me. And I would be able to manage to get it back, so I started sending out my invites and just barely got them done. Brought the computer upstairs, left it plugged in overnight, not knowing what was the problem. The next morning, Tuesday morning, this was a week ago, Tuesday, I was in half hour or so into my first class, and it died, and it did not come back. I could not get a single light to come on. I have a series of 7 lights here. I don't know what the first one is. The second one indicates battery. I mean, the plug is plugged in. The next one's a hard drive. The next 2, 3, 4 are batteries, and I couldn't get any of the lights to come on. They just, nothing would show. So I feared it. I hoped it was the converter, So my wife ordered a converter and a backup battery, and a new battery, because my battery was weak. I knew that. And so that knocked out the rest of Tuesday's classes. I met with some of you, including this class, on my wife's iPad, because that's all I had, but we couldn't do anything. We didn't have PowerPoint. It didn't have writable screen. It didn't have Screencast-O-Matic. It didn't have anything, and we decided just to call it quits and see what would happen. Well, my wife was busy getting from UAB, where she works, a free version of Windows 10. She put it on an old computer that we had here that had Windows Vista, which is a terrible operating package. Nothing works on it anymore, but we just did little things like emails and stuff like that. That still worked. But to teach from, I couldn't use that. So she got the Windows 10, which is, I know that one of you, I don't remember if it was a Perrin or Josh or somebody, had Windows 10, said you use it, and it seemed okay. The version we had was really hard to navigate, for me anyway, and to get things done. But anyway, we managed to go through that. So we were doing on that until Tuesday of this week. And at 11:20 Tuesday morning of this week, our internet went out. Not just ours, but the whole area here of Spectrum users. And in fact, Karen saw a diagram that showed it going over into Georgia. Now we found out that west of here, Pleasant Grove and Bessemer, people with Spectrum still were able to get internet. Over here, we couldn't. So now, not only was my computer down, my internet was down. Well, Karen had a hotspot, so she was trying to use that, but we have such terrible reception for cellular here. We're down in a hole, kind of, that her hotspot wasn't very strong. And just with one person on it, it was really weak. When two of us tried to get on it, it was terrible. And in fact, that other computer that I was using, it would hardly stay on at all. And so I started using her iPad again. And because it's iPhone and iPad, they seem to communicate better. So I was able to use her hotspot, but now I didn't have Blackboard. So it was a miserable way to try to do, but we managed. Okay, sort of. But then yesterday, after my second class, before my third class, I had a 20-minute break. I went downstairs, and right when I got to the bottom, she said, "You won't believe this." I said, "What?" "The internet just came back on." We went, "Oh, wow." Yeah, we were both so happy because we were using her hotspot, and it was terrible. Okay, Tiffany is here. Good to see Tiffany. Okay. Tiffany is here. Has anyone else had it? I think that's number 9. Yeah, we got 9 people. Okay. So we got the internet back, and then we heard something. Karen said, "Did something fall?" I said, "I don't know. I heard something too, but I don't know what it was." She said, "Could it have been a package?" I went to and by the way, on Monday of that week, when FedEx had misdelivered the package, I don't know what they did with it. They claimed they can't find it. The guy, one of the drivers said, "Hey, when they get messed up, we just tell them to send another one. We don't even bother trying to look for them." So they didn't bother. And so we had called back the company that Friday night when FedEx hadn't delivered. And Monday morning when they got into the office, they saw it. And by 7:22, they had sent out another one. Well, that got here yesterday afternoon. In that same 20 minutes that the internet came back on, I got my adapter, I got my battery, I ran up here and got everything set up and taught the next 2 classes as normal. So I've got that again. We're back in the saddle again, with just like we were when we left campus. Same computer, writable screen, Screencast-O-Matic, the whole works. All right, still only 9 students here so far, so let's get going. If y'all see anyone else add, let me know. How are y'all doing? Any issues, complaints, problems, jubilation, anything? Everybody okay? All right.
Yes.
All right. Like I said, last time I was on, when it finally would come up, I was on Karen's iPad and we were just talking through issues, working problems on a piece of paper and showing them in the camera. That was not the greatest way to go, but we did get through. We couldn't have PowerPoint, so I showed you in the book this last PowerPoint. Now I can't get this to advance or retreat. Okay. I showed that figure that was in the book, a really great figure to use. Okay. And then the next one, this wasn't in the book, and I thought we'd start with this today. This summarizes what we were doing last time. Whenever you have a phase change, the key here, there is no temperature change. If you're within one phase, add or take away heat, temperature changes. But if you're going between phases, the phase changes, but the temperature doesn't. So when you're going from a solid to a liquid, you're dealing with latent heat, and that's the latent heat of fusion. Okay? Think of that as freezing or melting, either one. The temperature at which that happens is sometimes called the freezing point or sometimes called the melting point. It's the same. Say for water, that's 32 Fahrenheit or 0 degrees Celsius. Okay? That temperature at which the phase changes, like liquid to solid or solid to temperature, is that fixed point, and it doesn't budge as long as the phase change is in progress. Okay? Now, so it's melting point if the heat is increasing. It's the freezing point if the heat is being taken away. So that's what this is showing. So let's go to liquid to gas. The latent heat you deal with there is the latent heat of vaporization. And just as a touch point, the latent heat of fusion is quite large. The latent heat of vaporization is enormously larger for most materials. I can't say for all, but for most common materials, the latent heat of vaporization much larger than the latent heat of fusion. We call this L sub F. This one's L sub V. Now that works, and when it's adding heat, that's called the boiling point. At the boiling point, the temperature does not change until all the liquid has become a gas. Or, going the other way, the temperature doesn't change until all the gas becomes a liquid, and then it's called the condensation point. Those are the same temperatures, okay? For water, that's 100 degrees Celsius, 212 Fahrenheit. And then, and there's Kurt. Welcome, Kurt. Okay, let's see what we're up to now. Up to 10, I think that's right. Yep, 10 people. Okay. So, just to let you know other issues that are going on, when we didn't have internet, it was very hard for me to access Blackboard. I didn't know what was going on, but I wasn't able to do it. I talked with the gal, the lady who's in charge of that, Dr. James, yesterday morning, in fact, to tell her I was having trouble doing Blackboard. Was it stable? Was there any problem with it? And she said, no, if you're running off a hotspot, you're not going to have enough signal to get Blackboard. So that's why I'm worried about this afternoon, and I wonder if something happened, because I had posted the announcement, the invite, last night, and then today when no one showed up, I went back to check, and it was almost impossible to get into Blackboard. But when I finally got there, it showed it was there, but not posted. So something happened either last night or this morning, and it seems like still Blackboard is not too good. Now maybe it's our wireless is not doing well again, our internet may be weakening, I don't know, but anyway, that's why you didn't see the invite until this afternoon, because even though I posted it, it didn't acknowledge it as posted. It said last night fine, but then today it didn't say fine. So, we got another student. Let's see who this is. Jacob Dove is here. Okay. Has anyone else had it? That should be 12 now. 3, 6.
I'm here, Mr. Fogg.
Who is this?
Jose.
Jose. Excellent. Okay. All right. So now we're up to 12. 4, 8, 12. Got it. All right. If you see anyone else that shows up, I won't always see them because I've got the screen full of Screencast-O-Matic, PowerPoint, and everything else. So let me know. So anyway, we're back running again. I've got my computer back up. I can write on the screen. I can do Screencast-O-Matic. This will be recorded and sent. We're back in the saddle again. So we were just talking about this slide, phase changes. Anytime you go from a solid to a gas or a gas to a solid, that's called sublimation. No matter which way you go, and it's called the sublimation point. Most things, common things, don't sublime going straight from a solid to a gas. They usually go through the liquid phase. Okay? Yeah. Oh, Ian is here. Is that right? What'd you say?
Yes, sir.
All right.
I'm here.
Okay, got you. And let's see how many that gets us up to. 13, that's right. Okay, that's how many I've got. So let me know if anyone else shows up, because I won't always see. Okay, I'll usually hear if they say something, but I won't always see. So any questions on phase change? The next subtopic in the chapter, and this is on page 105, or somewhere thereabout. Okay, every time I do something with Zoom, then I can't advance the slide until I go back and touch the slide. Okay. Top of page 105, evaporation and condensation. That was just mentioned in the last slide, and sort of a clarifying point here. Individual molecules can change phase at any time. If they have enough energy to do so, they do. That's why, and I was almost expecting someone to object to what I was saying before, water evaporates at any temperature, doesn't it? Okay? It doesn't have to be at 100 degrees Celsius or 212 Fahrenheit. Water will evaporate at any temperature. How do you account for that? Well, remember what temperature is. Temperature is the average, or is correlated to the average kinetic energy of molecules. But you see, individual molecules have a whole wide range of kinetic energies. I think if you go back several slides, let's see if I can find it quickly. I don't think I can, but I'll try. There was a slide with I'm not sure it's going to be here. No. May show up going this way. It doesn't show up going backwards. Yeah, there it is. Okay. This slide indicates, and I don't know, can you see the dot there? Wait, it's not there now. Okay. Okay. Okay, can you see the dot here moving on the graph? Yay or nay? Can you see that dot? You can?
Yes.
Okay. Now, this is all one material at one temperature. The average kinetic energy, which is related to the speed by 1/2 mv squared, this is related to the one temperature. But you see, you have some molecules up here going at incredibly large speeds, and some back here that are sluggards. They're hardly moving at all. They are always moving. The bulk of these are in this range. This average kinetic energy would be what determined the temperature of that material. But because you have molecules that are going much faster, individually, they have enough kinetic energy to escape, to evaporate. So that's why water, you set out a pan of water, some of it is going to evaporate, even though it's not at boiling. So just to let you know, a little bit of condition that goes along. I'll get there in a minute, several minutes. Okay. With this, you do not have to be at the boiling point for water to evaporate. The individual molecules may be enough energy to evaporate, but the entire body of water doesn't have to be. You'll still be evaporating. And that's why they say individual molecules can change phase at any time. If that highly energetic molecule happens to get enough energy, there it goes. So evaporation is the energy required, well, this isn't quite right. Evaporation relates to the energy required to overcome the phase cohesion. So the individual molecule may be at high enough energy to evaporate, whereas the average kinetic energy is not for the whole body of liquid to start changing to gas. The higher energy molecules near the surface can escape, and they do. Okay? Now condensation, that's going in the other way. Gas molecules near the surface may lose enough kinetic energy to become a liquid molecule again and merge in with the rest of the liquid. Now you don't see that happening frequently unless you have a cold glass of water in the summertime here in the South where the humidity is always high. Put that cold glass of water, tea, or something, especially if it's a glass, out, and immediately you'll see the condensation form on it. Those the water molecules in the air, they get close to that lower temperature glass, and there they start coalescing, merging with the other molecules and forming a liquid again. So yeah, condensation doesn't have to be at 100 degrees Celsius or 212 Fahrenheit. It will happen at any temperature when the kinetic energy of those molecules floating around in the air slow down enough to change phase and become a liquid. Okay? Here is an illustration of this. These numbers don't mean anything but relative energies. Okay? This is a beaker of water. Now it indicates you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules in there. You know you've got more molecules than that. They're only indicating 10. The average kinetic energy of that water with 4 5s, 3 10s, 1 15, and 2 25s, add all those up, 25 and 25 is 50, 65, 75, 85, 95, 100, 105, 110, 115. Add those up, divide by 10, average kinetic energy 11.5. Now that's going to measure some temperature. Average kinetic energy 11.5, that indicates it's at some temperature. Average temperature, of that water, because it's average kinetic energy. However, these two highly energetic molecules up here, because they're bouncing around more, they've risen to the surface. Actually, this 15 should be closer to the surface, the 10 should be, the 5 should be further down. But in general, the water is always mixed. But those two 25s happen to be at the surface. That may be enough energy for them to escape. Now, if they do escape, you've lost 50 units of average kinetic energy. So you subtract 50 from 115 and you're down to, 65. Divided by 8, and that's what we have here. Your average kinetic energy is, and Jacob Porte is here. All right, welcome. Oh, and Kaya is here. Good to see you. Okay, and Jacob Porte. Is someone else? Okay, let me see how many we got now. 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Got it. All right. Let me know if anyone else pops up that you can see that I don't. Okay? So now you've lost the two biggies, the 25s, you're down to an average kinetic energy of 8.1. I guarantee you that's a cooler temperature than it was up here when your average kinetic energy was 11.5. Now, you've probably experienced this, frankly, anytime you get out of the shower or a tub, you immediately feel chillier, right? And why is that? That water that's on your body now starts evaporating. And when it does, it's no longer the same temperature it was when you were in the shower or the bathtub. It is now at a lower temperature because the higher energy molecules have escaped, leaving you a lower average temperature. You can probably think of other and maybe better examples than that, but that's certainly the case. Any questions? So evaporation condensation can occur at any temperature because all it takes is individual molecules that are either high energy or low energy. High energy to evaporate, low energy to condense. And it doesn't take the whole body to be at that same average kinetic energy. All right. That said, we're moving, and by the way, there is a picture on page 105 of a Listerine bottle. If any of you have ever tasted Listerine, you know that it has a fair amount of alcohol in it. Not the alcohol you want to drink, but some form of alcohol. Alcohol typically has a lower condensation point than water, so the little droplets there are forming on the inside of that bottle because the average kinetic energy of the Listerine in the bottle, some of those molecules are enough that they escape, but then if it's in a cool room like an air-conditioned room, then the bottle will be cooler and they recondense on the inside of the bottle. And then on the top of page 106, I don't know if any of you can remember when people used to hang out their clothes to dry, but they used to do that. I used to call it solar clothes dryers, okay? It was a very modern thing back in ancient times, okay? But there are 4 factors it said that are influence the time needed to dry these clothes. Number 1, temperature. The higher the temperature, the more rapid the evaporation rate will be. Number 2, surface area. If you spread them out, don't have them touching each other, they will dry more quickly. Okay? Number 3, wind. Now, we were talking about this last time. I don't remember which one it was. It seemed like it was maybe Josh or Perrin or something. Yeah, Josh, I think it was. Talking about goosebumps, they sort of increase the and I call it boundary layer of air that's trapped near your skin. Well, that's the same thing here. When you have a wind, and this is why fans work. I just turned off my ceiling fan because it was a little too cool for this afternoon. I thought the room was warm enough I need it, but it was a little too cool. Why does a fan work? It's blowing air across you, and that fresh air that comes across removes moisture from your body. Whether you realize or not, you're always secreting moisture through your skin. Always. You certainly know it when you're sweating. You realize that. But you don't realize there's always moisture coming out of the pores of your skin. But most of the time, it's rapidly evaporating away. That's what keeps us, you might say, that's the body's air conditioning system. That's how we keep from overheating. And when you're really out there working hard or exercising or whatever, you're now producing water faster than it's able to evaporate, and that's why you sweat. You're always sweating. I would say even in the wintertime, you're sweating some. You may not realize it. It's evaporating as soon as it gets to the surface. Okay? So the more surface area you have, well, we'll go back to that later. But if you have wind blowing, like a fan, now it's blowing fresh air off, and that surface, that boundary layer of air that's against your skin, it's getting blown away. So it's faster evaporating the moisture that's coming out. So that's why a fan Back in the old days in church, that's all you had. You waved the fan at yourself and tried to keep cool. Okay? Altitude makes a difference. And this may not be quite as obvious. Has less atmospheric pressure and therefore allows water to evaporate more easily, water vapor to escape more easily. So down here where we live, we're right at 1 atmosphere of pressure. Okay? So we have a little more trouble cooling off than you would at a higher elevation. So those are the 4 factors that influence drying clothes. We aren't talking about all those in this text except right there under the picture. So let's move to area 4.5, section 4.5, and this is thermodynamics. A decent definition of the term, oh wait, let me just ask you, what does the prefix thermo mean to you? A few days ago, slides ago, someone answered heat. Right, very good. Okay. Dynamic, what does that mean to you? Something's changing, stuff's going on, okay? I think of motion. Think of dynamite. Something big is happening when dynamite explodes. Major changes are occurring. So thermodynamics basically means the change of heat, okay? So here's the definition: the study of heat and its relationship to mechanical and other forms of energy. Now, on an earlier slide, you may remember this said in the macroscopic sense, the study of heat and its relationship to mechanical and other forms of energy on the macroscopic scale, the big scale, okay? Now, thermodynamic analysis includes the system. You have to kind of identify what system you're dealing with. But not just the system, the surroundings of the system. That's everything outside your system. And you have to look at the internal energy. That's the total internal potential and internal kinetic energy of the object in question. That's where it gets onto the micro scale to some extent, the internal energy. Now, involved in thermodynamics is energy conversion, because remember, we said it's the change, the dynamical activity of heat. So what are the energy conversions? Well, here's some of them. Friction converts mechanical energy into heat. And we gave the illustration, I think it was last class. That's what your brake drums and brake pads do. They take the mechanical energy of the car, the kinetic energy of the car, and by pressing together, they produce heat. And that's a large amount of heat too, usually. Now, and I was going to ask this question. I don't think I ever got it out because I think we lost continuity at that point. But on either hybrid cars and possibly electric cars, what is different about your braking system? Some of you work on those? Anybody? I know Kaya and Tarsha work on the brakes all the time, don't they? Okay. That is typically called, let me see if I can get the right word, regenerative braking system. Y'all heard of that word before?
Yes, sir.
Okay. Now, what is going on there? Rather than friction slowing and converting the mechanical energy into heat, what you have is very strong electrical inductors. Basically, a generator. Because generator takes mechanical energy, specifically kinetic energy, and makes that into electrical energy. So if you have a strong enough fields and things like that, then you can use that to convert the mechanical energy of the car into recharging your battery or your energy cells, whatever you happen to be converting to. All right. So it doesn't have to be Friction is one way to convert mechanical energy. More efficient way is to convert it into electrical energy. All right, another energy conversion is a heat engine. There's your internal combustion engine. That's what most of you work on, okay? These are devices that convert heat into mechanical energy, kind of the reverse of that. You take the heat of the exploding gases in your cylinder, pushing the piston downward, that's giving it mechanical, specifically kinetic energy, and that turns the drive shaft, turns the wheel, makes the car move. Okay. Other application, heat pumps. Now what a heat pump is doing, and I'm going to combine this somewhat with refrigeration too because they're the same process. The first step in a heat pump or a refrigerator, anyone know, or an air conditioning system, what's basically the first step? You compress a gas in the compressor, right? You got a compressor in an air conditioning system, you got a compressor in a refrigerator, you have a compressor in a heat pump. First thing you do is compress the gas. That's a mechanical process. And in doing that, you're producing heat. Basically, friction between the gas molecules. Now, say it's a gas, we call it sometimes just call it a refrigerant. But aren't those always gases? Now, maybe they're stored as liquids, but in the system, they're gases. And when you compress a gas, the molecules are now closer together, they're moving, bouncing into each other, they're producing heat. And what a heat pump does is take that heat from the compression of the gases and pumps it into your house. Blows the indoor air over those, sort of like a reverse radiator to take the heat away from that and heat the house. Now what refrigeration and air conditioning does is take that excess heat that's been produced and blow it outside, blow it to the surroundings. Remember, you have the system and you have the surroundings. In the first case, when you compress the gas, you take the heat and pump it into your surroundings. That's where you want it to be. On the other case, when you're doing refrigeration or air conditioning, you blow it to the external surroundings because you want to get rid of that heat. And then what you do with refrigeration and the cooling part of a heat pump, you let the gas expand, usually fairly quickly, and whereas compressing a gas produces heat, expanding gas absorbs heat. So that's where the refrigeration comes from. That's where the air conditioning comes from. From that expanding gas, now it's absorbing the heat out of your room, out of your building, out of the back of the refrigerator, okay, or the inside of the refrigerator, okay. Now, they mention here other energy converters, organisms. Did any of you eat lunch today? Hopefully so. What are you doing right now? Your body's doing is taking those carbohydrates, maybe a few fats, okay, whatever you consumed, and you're converting that stored chemical energy in those products into motion, into electrical impulses. That's what allows you to hear, see, smell, well, not that kind of smell. Well, never mind. Okay. Those are the organisms. You are an organism. You are a thermodynamic body. You are converting right now stored chemical energy and also converting it into heat. That's why your temperature is 98.6. The room around you is probably closer to 70, right? You're hotter than the room. Why? You're dynamically changing the heat regime. Hurricanes do the same thing. Hurricanes pick up energy near the tropics, okay, right around the equator, and bring that energy big time up to the more temperate areas, such as where we live, okay, the Gulf of Mexico, the East Coast, or out in the Pacific, anywhere, the huge Pacific Ocean out there. A hurricane is a heat machine. It picks up energy from the tropics and carries it up to the temperate region. I go to the same church that Jerry Tracy goes to. He's the weatherman for Channel 13. And I was in a book study. We just happened to be in the same book study. I only went one time. I don't know how many times he went. But that first night, someone just asked the sort of rhetorical question. Well, I don't see why there's things like this hurricanes that cause so much damage and people lose their lives and stuff like this. And Jerry just couldn't help himself. He said, no, if we didn't have hurricanes, we wouldn't be able to live on this planet. Because hurricanes are the device that move huge amounts of energy away from the tropics into the temperate regions. And by doing that, they keep the tropics from getting too hot to support life, and they keep the temperate and the polar regions from being too cold to support life. If we didn't have those heat machines, hurricanes, we wouldn't make it as a planet. So I had never quite heard it phrased that way, but it stuck with me ever since. Stars, including our sun, those are heat machines. Those are nuclear reactions going on in them. Matter is, specifically hydrogen, is being fused into helium, and when that happens, little teeny bits of matter are converted by Einstein's famous formula, E is equal to mc squared, and you can't write on this screen in a dark pen, so I'm going to write in yellow. You can't read it with a dark pen, but that's what his famous formula, E is equal to mc squared. Little, minute amounts of matter, mass, from the collision and the fusion of those two atoms are released, and then multiply that tiny amount of mass by the speed of light squared, which is an enormous number, you get a lot of energy out of that. Now, black holes, on the other hand, they seem like energy sinks, whereas a star is emitting energy big time, all the time, 24/7. Black holes are sucking it in. The reason they're black, light can't even escape a black hole. They're big energy sinks. In virtually any system with energy input and or output, that's a thermodynamic device in many sense. Okay. Now, I think I may have mentioned before, let me just check and see if we still are at the same number. 15 participants. I think we actually lost someone, didn't we? Yeah, we are at 15.
You scared
Okay.
them off, Doctor.
What's that?
You scared them off.
Oh, yeah, I'm bad at that. Okay. There are actually considered to be 3 laws of thermodynamics. Some people add a 4th law, but since it's basic to even the 1st and 2nd and 3rd laws, they often will call it the 0th law of thermodynamics. So they, rather than doing 1st, 2nd, 3rd, and 4th, they do 0, 1, 2, and 3. Okay. This book doesn't mention that. I may mention it in passing, but we'll leave it alone. The first law of thermodynamics is basically another statement of conservation of energy. Basically, energy is neither created nor destroyed, but it changes form. So the first law of thermodynamics often talks about in terms of internal energy, which could be either kinetic or potential energy within the system. The heat, that's usually something that goes out, but sometimes it comes in, okay? And then work, which usually is something that goes out, but sometimes it's coming in, okay? It's stated in terms of the changes in the internal energy, okay? Now, one application is heat engines. We're going to come back to that in a minute. Let's see what they say about the formula here. Well, they don't say it, okay? If they don't give it, I will write it down, okay? But here is the example of what's happening. You have a piston here, and originally it was at the top of this cylinder, okay? At the top of the cylinder. You put a weight on it. Well, a weight is a force. That's the mass of this object times the acceleration due to gravity pulling that downward. And that weight is compressing the gases that were in that cylinder. And by compressing the gases, you're increasing their temperature. Okay? So the piston is moving down, compressing the gases, increasing the temperature. The change of potential energy that you would have here, from up here to down there, is equal to the increase of heat energy, thermal energy, that would be in the gases. Okay? But then you bring a flame and put it under that cylinder, and now the air molecules start moving more aggressively. They bounce off into each other more vigorously, pushing each other further apart, and they push the weight back up to the top. So now you've got heat added here through the flame, acting on the system, doing work on the weight. Okay, whereas before, the weight did work on the gas and produced heat. You add more heat, now the heat does work on the piston and changes its potential energy back again. Okay? But you had to add energy to make that happen. But you didn't create energy, you just changed its form. Okay? The flame heat does work as the heated air expands and lifts the weight. So the change of potential energy here, that's your equal to the amount of heat that the air has picked up inside the cylinder. Okay. Now, here is the model, you might say, for your first law of thermodynamics. And this is where the heat engine comes into play. What you do, you start with low temperature region. Okay? For you in the automotive industry, that's the air basically that you suck in through your air filter, right? That's going into the system. You have a high temperature range. That's when you take that air that you've sucked in, use the oxygen from it to ignite the gases, and suddenly you have a high temperature region. Okay? Now, I said it's through the air filter, the air. This is also the same low temperature region that's outside the car in general. Okay? So then the explosion happens, and you, the high temperature, what your heat engine does, that's the internal combustion engine, it does work by making those pistons move, making the drive shaft turn, making the wheels turn. That's the work that comes out. But you always have some heat that is not used to do work, but that goes down in the low temperature region and raises the temperature there. Now, where are two of those low temperature regions? One is in your radiator. Your radiator is sitting there initially, when you don't have the engine on, at ambient temperature. This morning it probably was in the high 40s. This afternoon it's in the 70s. Whatever it happens to be, okay? It's been sitting there long enough, it's in that region. But some of that heat, a lot of it, you wanted most of it to go to doing work, it didn't. Most of it goes down here. So it first hits the radiator, then the fan, your radiator fan, pulls that cooler air, that low temperature air, through that, removing that excess heat, that heat you weren't able to get any work from, and blowing it into the environment. So you're raising the environment just a little bit. More of that, or some of that high temperature, goes out the tailpipe. Don't be feeling of the tailpipe. It's going to be hot if you run the car very long, because you have a lot of heat going out there too. Those are your low temperature regions. The surrounding area where you're heating with the radiator or heating with the exhaust. Only some of that work goes to moving the car. Unfortunately, a pretty small amount. I can remember hearing the number tossed around back when I was in high school or college age, the cars being maybe at best 20% efficient. That 20% of the work of the heat actually does real work, and probably 80% is blown to the environment or wasted some way. But even that does work, as soon as you step on the brakes, you're losing that kinetic energy, and now that's going to heat, and that's going to the environment. So you're losing all the way around. Now, I'm sure today's cars are much more efficient than the ones were back when I was growing up, but I still doubt if they're much more than 25% efficient. Have any of you heard any numbers? They may not talk about this much, I don't know. Okay, that's an example of a heat engine using the first law. The conservation of energy, the high temperature region here, some of that energy does work, the rest of it increases the low temperature region, which is your environment. You don't gain or lose any energy, you just change its form. Okay. And where this came from, stored chemical energy in the fuel. Petroleum, diesel, whatever you're burning. Okay. Peanut oil, whatever you're burning. Okay. Now, this place here, I think, is where they should have put the formula for this. The basic formula here, and this is I don't like the way the book expresses it, but it's fine. The change in internal energy. So internal energy is usually given the symbol U, and I'm not really sure why. Okay? So U1 would be initial internal energy. U2 would be the final internal energy. So the change of internal energy, change is difference in or subtraction, delta U, you might say, which is U2 minus U1. Okay? Final minus initial. Always that's what the delta stands for. Okay, where does that go? Okay? One place it goes is to heat. Okay? The change in internal energy, some of it goes to heat. The rest of it goes to work. Okay? Now, usually heat is added to the system. Not always, but it could be. So, rather than calling it Q, they call it JQ. Now, I told you we'd be coming across this again. What the J stands for is mechanical equivalent of heat. Because if you're talking about this in energy terms, that's probably in joules. Okay? If you're talking about heat, that's usually in calories or kilocalories. So you use the joule equivalent of heat to change the calories to joules. That's what JQ stands for. Okay? They didn't do a great job of explaining that, though they do sort of say it. But that's the joule equivalent of heat. Just to remind you, and I don't like that they use it because this is the symbol for that, J, and that is related to 4.184 joules, which is also capital J per calorie. And that's a little c calorie. Okay? You could change that to kilojoules per kilocalorie, use the same number. That's what this J is. That's not the unit joule, it's the joule equivalent of heat. Okay? And then they usually write this with a minus W. Okay? Because generally you increase the heat of your system, but then generally you do work on the environment. So your work is being lost, which is good. That's what you were trying to produce, but the heat is kind of just wasted. So the change of internal energy either goes to heating up the environment, which is a plus thing, or doing work on the environment, which is a negative thing. Okay. Now, if you have a situation where your pretty sure they're saying the internal energy is the same, that U2 minus U1 is 0. So in other words, this is a steady state situation. You don't have any energy coming in, you don't have any going out. Well, if that's the case, then you can solve this W, put it on the other side, and that's equal to that joule equivalent of heat, but now you have a change of, this is that Q high minus Q low. Okay, now this is true only if these two are equal. Then this is 0, move W to the other side, and now you express your heat as the difference between the input and the output. Okay? If you go back to, no, I'm sorry, to this slide, there's your QH, there's your QL. So the change in those equals the joule equivalent of that change of heat. You see the Q high minus Q low, any that doesn't come down here goes out there. So that's basically what it's saying. That the change of heat here between the high system and the low system, the change, some of it's wasted in the low system, but that difference in this, that produces the work. And you multiply the calorie times joule equivalent of heat, this, and that's how you get how much work you've done. So those are the two formulas they use with the first law of thermodynamics. Really exciting stuff. I can tell y'all are impressed, right? All right. Now, let's move to the second law of thermodynamics. There are three equivalent statements here. You probably could come up with a few more. But here are three equivalent statements that describe the second law of thermodynamics. The first is, sounds sort of nebulous, no process can solely convert a quantity of heat to work. It just doesn't happen. You always have some of that QL, that low-level heat that's wasted to the environment. You can't help it. That's one statement of the second law of thermodynamics. No process can convert a quantity of heat completely into work. That would be like in a heat engine. You always have that heated exhaust, that heat in the radiator that's wasted to the environment. Here's another way to explain this. Now, this doesn't sound like it's saying the same thing, but it really is. Heat never flows spontaneously from a cold object to a hot object. That just doesn't happen. In other words, you have to force it to happen. Okay? And that's what a refrigerator does. You make that heat come out of those colder things and go into the hotter room. That's what refrigeration does. In the big picture, you're forcing that to happen. It's not happening spontaneously. Now, this one sounds even further removed. Natural processes tend toward a greater state of disorder. That state of disorder is called entropy. Okay? Natural processes tend toward a greater state of disorder. Now, occasionally, as I watch these videos, as I give these things, and sometimes people will pop up, and sometimes they'll be, it looks like possibly in their bedroom. Some of you may be in your bedroom now. And I just wonder, the natural processes of living in your bedroom, does it tend to get neater all the time, or does it tend to move to a greater state of disorder? Anybody have the former, or is it always the latter? Always the latter, okay? They never move under their own natural process toward a state of order. They always move to disorder. That is called entropy. The entropy is increasing. Now, one really, I guess, simplistic way of looking at this, let's say that sometime in the past, you went out to the drugstore, the dollar store, somewhere, and bought a deck of cards. You opened the box and took those cards out, and I bet you the cards, probably one end or the other, started with the ace of spades, went down to the deuce of spades. And then you got the ace of hearts down to the deuce of hearts. And then you got the ace of diamonds down to the deuce of diamonds. Then you got the ace of clubs down to the deuce of clubs. Right? Something about like that. and they were all facing the same direction, and they were all in regular, very systematic order. Right? Now, I want you to imagine you throw away the box or get it out of the way. You have all the cards there. They're completely loose. You put them in the middle of a sheet, and you get 3 friends, and the 4 of you toss that sheet into the air and let the cards, keep them on the sheet, but let them just go up and down as many times as you want. Now, how many times would it take until that deck of cards happens to fall back into the middle of that sheet in exactly the same order that you started? Never happen. You'll never even get those deck of cards to all come down facing the same direction. You'll never get them, hardly ever get 2 of the cards that are consecutive to each other. It just doesn't, I mean, that can happen under just randomness, that they could be consecutive. But you'll never, ever, ever even get them back into a stack. They just won't do that. They always, in natural processes, go to a state of greater disorder. Now, they give some other examples, and we'll get to those later. But that's one. Your bedroom is a pretty natural one, too. Okay. 2 reference scales. Okay. First is the object's external energy. That's the energy of the global coherent motion. Think of throwing the baseball. Okay. Yeah, well, the whole baseball goes together, and it all goes at the same speed. It has the same mass. That's the energy of the global coherent motion, external energy. That's associated with work. You did work on the system, and it took off and went. Remember that illustration not too long ago of the bowling, okay? You give that energy to the bowling ball, it goes down and gives it to the various pins, and they all go flying around in different directions. That's energy of a global coherent motion. When it hits the pins, they don't look very coherent, but they still individually are coherent motions. That's associated with work. The work you did on the ball to send it down the lane, that work it then transmits to the pins, sends them flying in all directions, and then the ball itself hits the back and it goes whoop. You've heard that before. Okay? The second reference scale is the object's internal energy. That's the energy of the microscopic, chaotic, incoherent motion. That's what's associated with heat. So you see, you do work on a system, you will get coherent. That's what you're trying to get. That's what your internal energy is trying to get your car to move down the road. Coherent global motion. But what happens always, you have some internal energy, microscopic, chaotic, incoherent motion, that heat is lost. You'll never get that back. Okay? We get some of it back if you use regenerative braking. Yeah, you get a little bit of it. You still have heat though. Okay? You still have always heat. Okay? There's the second law of thermodynamics, 3 different ways to express it. Here are 3 examples using those 3 different statements. First, the first statement. You can think of this also as conservation of energy. And let's imagine a heat engine, like your internal combustion engine. Your input energy is that stored chemical energy that those plants stored up many centuries, millennia ago, and they got processed by bacteria and heat and pressure and all sorts of things, ultimately to become some type of petroleum product that later we distilled and amplified and got into something you could burn in an engine. Okay? That's what you got. That energy, that internal stored chemical energy. Okay? Now, that energy is equal to your output energy. Once you light that explosion in your cylinder and you start doing work on that piston, but also producing heat, all that put together, the work that you've done, the heat that you produce, all that is your output energy. The input energy equals the output energy, conservation of energy in a heat engine. But here's where the second law differs from the first law. The efficiency of a heat engine is the work done per unit input energy. Now remember, we said your input, I want to call that EI. That's the input energy. That's the stored chemical energy in the chemical bonds of that petroleum. Okay? That's equal to the work done. That's moving the car down the road. Plus the excess heat. Now you'd have to have your J in there for joule equivalent heat and that kind of stuff. But that is your input, and there's your output. But what the efficiency is the output work per unit input energy. So basically, if you divide both sides, we'll get to it later. So the work done per unit output, so that's work over the input energy. That's what we're dealing with here. And guess what? Because there's always some wastage there, this is always less than 1. Can ever equal 1. It's never 100%. Okay? So here's what the second law says. The efficiency, and this is what now I hate that I used EI. This is called the efficiency of the engine, is always less than 1. Some energy is always degraded as heat. Always. Okay? Now, some machines do better than others. I think somebody mentioned in earlier weeks ago a hydraulic jack. Boy, hydraulics transfer, and they do just about as efficient a job as just about anything I know. There's always some pressure in there, always a little bit of heat. You never measure that, but generally, whatever you pump up, when you're pumping that hydraulic jack, it almost is always doing very close to the same amount of work out. However, if you were to check that fluid in that jack, you would find out it is heating up a little bit, but not much, because you are compressing a liquid, and that always creates some heat. So some heat energy is always degraded. Internal combustion engine, that percentage is pretty low. Hydraulic jack, that would be very, very efficient. Not ever 1, but very efficient. Okay, I think I need to remove my writing here. And here's basically what I just said. The Q from the high side, that's the energy of the input energy. That's the stored chemical energy of the fuel, say, is equal to the work done to move the car plus the Q that's lost in the low energy side. Okay? You'll always have some loss. Okay? And what the efficiency, they use little e, now I remember. Little e is the ratio of W to capital E, and guess what? Capital Q, that's always, always less than 1, because you always have some lost energy. Okay, so there's the second law of thermodynamics, that first statement. First statement back here, which is no process can solely convert a quantity of heat to work. Just doesn't happen. So here's the second statement. Same second law, second statement. Conservation of energy. Again, this is in a heat pump. The energy arriving at the high temperature region is equal to the energy from the low temperature region plus the work needed to move it. Okay? Now, think of this as that first step in your refrigeration or cooling process or heat pump process. You're compressing a gas. The gas always starts with some temperature, right? Always has some temperature to begin with. That's the QL. You're doing work on that gas, compressing the gas, and now it moves to a higher temperature region. So now that's the compressed gas inside the cylinder, or inside the compressor. That's what I should say, inside the compressor. The work is required to move the energy from the cold region to the hot region. Okay? Work is required to do it. It doesn't happen spontaneously. Okay? You always have to do work to make it happen. The energy arriving in the temperature high temperature region equals the energy from the low temperature region plus the work that you did to move it. The upgrading of energy by the heat pump is accompanied by the greater degradation of energy elsewhere. What energy did you use to do the work? You had to expend some energy to make that happen. That's why running your air conditioner is going to lower your gas efficiency, right? Because now you're not just moving the car forward, you're also having to compress the gas. So that's just one dumb illustration of it. All right, any questions? Corrections? Y'all know your systems better than I do. Okay. Then the second law, but the third statement. Real processes are always irreversible processes. Okay? The real processes, things that happen, are always irreversible. In other words, whatever is happening, you can't completely undo it. And that measure of disorder is called entropy. The second law in those terms say the total energy of the universe is continually, the total entropy of the universe is continually increasing. In other words, we're going toward disorder, okay? Always going to disorder. Now, maybe out there somewhere, there's some exception to that, something that changes back, but as far as we understand it now, no. We are going to a state of more entropy, greater disorder. Now, what does that mean? Natural processes degrade coherent, useful energy. Okay? Just like bouncing the sheet up and down, your cards get more and more mixed. Okay? The available energy of the universe is diminishing because much of it's going to that disorder. Eventually, and this is what they say, there will be the heat death of the universe. This is a proposition, not even a theory, I don't think, because we never can prove this. We can't test it, we can't measure it, but this is what they think. Direction of natural processes always move toward disorder. One, where I said the deck of cards, their favor is spilled milk will never unspill back into the glass, will it? Not gonna happen, okay? Everything goes to disorder, including your bedroom. All right. Now, that was the last slide in the chapter. Before we leave here, though, I think this one's a fairly weak concept applied. Why is it called a pop can? Frankly, I don't think this is why it's called a pop can, but maybe it is. You can read that. You might find it interesting. You might find it lame. I don't know. Go over to page 108. Myths, mistakes, and misunderstandings. It makes its own fuel. Boy, wouldn't that be great, wouldn't it? They sometimes call this a perpetual motion machine. And the bottom line, they don't exist. They can't exist. Not gonna happen. Ever. Okay? Because of the second law of thermodynamics, basically. Now, I've heard it said, well, what if you had mounted on the roof of your car a fan that turned a turbine that produced electricity? Could you produce enough electricity to run your car then? Would that work? The answer is no, because all the energy that's being taken to turn the fan came from the car to begin with. You got the fan up there that's going to slow your regular speed, and you're not going to get anything. In fact, you'll be losing energy because all natural processes tend to disorder. Okay? You can try various other things, never going to happen. That's why I think the experiment they did, I think in the automotive department, probably close to a decade ago, where they were trying to use the excess electrical energy being produced by the generator that wasn't being used to charge the battery, use that to hydrolyze water, capture the hydrogen, and then inject the hydrogen into the fuel system, and that explodes very nicely, okay, because hydrogen is very explosive. So could you be using some of the, you might think of wasted electrical energy to hydrolyze water and then to burn that hydrogen to help move the car? It's a good theory. It's a great theory. I don't think they ever were able to get it to work, probably because second law of thermodynamics prevented it. Now, there may have been some more practical reasons it didn't work. I can easily imagine that burning hydrogen in your cylinder, of course, the burning of hydrogen produces water, and even though it would be very hot steam, I still think that would probably be degrading to the walls of the cylinder and maybe your exhaust system and everything else. I don't know that for a fact. I don't know what the problems came, but I think they finally had to give up on it. Now, there's an interesting guy featured on page 109, People Behind the Scenes. And he is a really interesting character. I'm not sure I would have liked him, okay, but he's still an interesting character. His name was Benjamin Thompson. He was born in the U.S. before we were the U.S. We were British colonies. But he was born in the British colonies here in the U.S., born in Benjamin Thompson in Woburn, Massachusetts, okay, back in 1753, before we were a country. So he was not born in the U.S., he was born in what we call America, but we were the British colonies then. Okay, now, very bright guy, very, very bright guy, okay? Now, I don't know whether to tell his story first. I think I'll tell why he's in the book first. Well, that's hard to do. Let me give the rest of his story. When I was guessing he was about 23 years old, that would have made him right around 1776. That was when we signed the Declaration of Independence. Probably 75 was when the War of Independence started. And it went for quite a while, about till 77 or so. But at some time along that, when he was a young, early, mid-20s, he did not believe in the cause of the colonies. He was a good, faithful British citizen, okay? He did not think we should break away from Britain. He was not held in too high a favor, okay? And ultimately had to escape and flee to England, okay? He was a very bright guy. Remember that, though. Very bright guy. Quite a good engineer. Okay, now, I think I've read somewhere, I don't think it's here, but I believe I've read somewhere that they really felt that he was associated to some extent with a guy named Benedict Arnold. Y'all know who he was. His name is synonymous with being a traitor, because he was the
traitor of traitors.
Yes, he was. But from the British side, he was not. The rest of us were traitors, okay, because we were rebelling against Britain. He was not, and neither did Benjamin Thompson. But Benjamin Thompson fled and went to England, okay? And some of this is given here. I'll let you read it too. But anyway, he went to England and was rewarded with government work and appointed a lieutenant colonel in a British regiment. Now, I don't think they ever came over and fought here, but he was, like I said, a very bright guy. Now, he went to work in Europe as well as England, and he was such a good scientist and engineer that he was actually made a count of the Holy Roman Empire. Now, I can remember in recognition of civil administration work he did in Bavaria. So not just as an engineer, but there, civil servant as well. Now, I can remember my 12th grade English teacher, anytime she mentioned the Holy Roman Empire, she would say, which was neither holy nor Roman nor an empire. Okay, so every time I read it, I think of her saying that. But anyway, he worked for them. He was named a count. So that's why he's given the name Count Rumford. Okay, and I guess Rumford is a town near Concord where he lived for a while, and that's where he took the name Count Rumford. But that's his background. Here's what he did. He was an engineer, and he was hired by probably the Holy Roman Empire there in Bavaria, and as an engineer, he was put in charge of making cannon. And my understanding of how they made cannon back then, they poured the entire barrel into a mold, molten iron, probably was cast iron, I don't know for sure, into a mold, and it came out the entire barrel. But then they had to drill the hole in the middle of the barrel that you would fire the cannonball through. So that's what he was in charge of doing, making the cannons, and his job particularly was drilling the hole, and that had to be very precise, very carefully done, and it was a long and miserable task. Some poor old horse, I believe it was, had to go walking around in a circle, pulling or pushing on a thing that turned a big wheel that ultimately, through gears and stuff, ground a bit into the metal. Okay? It was a slow process. It was a miserable process. And the bits wore out pretty regularly. I don't know what the bits were made from. Obviously, harder metal than the metal you were drilling, but it was still going to wear them out. But Rumford, being the scientist and engineer that he was, he noticed they always got hot. Now, the newer the bit, the less heat, but the older the bit, the more heat. And before him, now here, we have to take a step back in time. Before him, remember good old Aristotle? He said there were 4 elements: earth, wind, water, and fire. Okay? Those were the 4 elements. He said those are all, that's what makes up every bit of matter on the earth. Earth, wind, water, and fire. Well, Rumford noticed that a newer bit wasn't going to produce as much heat, it always produced heat. An older bit produced more heat in the metal. Well, of course, they were thinking the heat came out of the metal. And he said, no, that can't be. So here was one of those breaks in the good old Aristotelian logic, and he said, no, this isn't right. So what he did, and remember this is Bavaria, this is near Munich, and Munich is not quite close enough to see the German Alps, but it's not too far either. It's just a few hours drive south from Munich, and you're into what they call the German Alps, high mountains. And what he did, he was somewhere down there drilling this cannon, and he took a defective cannon, probably the metal didn't do right, and it wasn't going to work, it had a crack, whatever it was, maybe the hole got off center, I don't know. He took a defective cannon. He took the oldest, dullest bit that he had, and he took his poor old horse who was doing the turning, and he poured the cannon, the barrel, full of the coldest water he could get from the Alps at that time. Cold, almost ice water, put in the cannon. Got the horse to walking around in a circle, and within, I think, just a few hours, he had the water boiling. Okay? And what he showed there, that fire was not an element. That fire was a result of doing work on the object. So it was a form of energy. He was, as far as I know, the first to ever truly recognize that. Now, people have been drilling boring cannons how many times before, no one ever thought through, why is this getting hot? He thought through it and said it can't be. Later then came James Prescott Joule with much more careful experiments, and he came out with the Joule equivalent of heat. But I don't know if he'd ever thought of it if it hadn't been for Benjamin Thomson. Now, that Thomson there has a P in it. The William Thomson that worked with James Prescott Joule, that's without a P. So there's no kin there. William Thomson was from Britain, and so was James Prescott Joule. Benjamin Thomson was from the colonies, and he moved back to Britain. Okay. So anyway, interesting story. I'll let you read it. There was, and I almost forgot about this. Okay. There is here one more example. And let's hit that before we leave. A heat engine operates with 65.0 kilocalories of heat supplied. That's Q. Okay? But that's Q high. Okay? I think is what they call it. Yeah, Q high. And exhausts 40.0 kilocalories of heat. That's how much comes out of the tailpipe, you might say. Okay? And that's your Q low. Now the question is, how much work did the engine do? Well, if you remember the formula we had there, that work is equal to, now work is usually measured in joules, but this is measured in calories or kilocalories. So you're going to have to use the joule equivalent of heat, which they use the symbol J, which I found a little awkward, but it's okay, times Q high minus Q low. In other words, the difference of those heats, what you put in and what comes out, that has to be the work done. But you have to convert it to energy terms, and that's what the joule equivalent of heat, which is 4.186, I believe it is. 184, I'm sorry, 184. I don't remember numbers well. I teach math, I don't remember numbers well. Okay, does that make sense? This is joules per, kilojoules per kilocalorie. Now, they use the 4,000. I see no reason to do that. Let's keep it in kilojoules. Kilojoules per kilocalorie. Okay? And that's multiplied by the difference. And what's the difference in 65 and 40? 25?
Yes, sir.
25 joules. No, I'm sorry, kilocalories, sorry. I'm already making my conversion here. Kilocalories. Okay. This kilocalorie cancels that one. And what we have then is 25 times 4.184. Anyone got a calculator? You can do it. I've got one here, but I'm pretty slow with it. All right. 4.184 times 25 equal, that's about 105 joules. About 105, I'm sorry, kilojoules. My unit was kilojoules. I didn't see it there. Okay. About 105 kilojoules, which is 105,000 joules. Okay, approximately. All right, that was the last problem. Okay, there is another concept applied, thermodynamics in action. That's probably worth a read. I would be very careful if you're doing it, okay? If you're running a blender, mama's blender, in a pan or whatever you're running it in, and you have water in there and you put a thermometer in there, don't catch the thermometer in the blender and get mercury or alcohol and glass all over in your stuff. You're not going to be very popular in the kitchen. Okay, be very careful if you're going to try it. I Don't think I'd ever try it. Okay, but it's up to you. Anyway, that's the chapter. And as I say at the end of every chapter, nothing replaces reading the chapter. So please go back, read the chapter if you haven't already. And then once you've read it, maybe a time or two, whatever, look at the summary. The summary does a pretty good job of condensing most of the important things down into more manageable things, but you lose the context and all of why it happens. You just see the words here. So some of these words are italicized. Those are usually pretty important ones to note. It's a reasonably long summary, so that's pretty good. Summary of equations, there's actually 8 of those listed here. Most of those are pretty important too. The key terms, I would say probably not quite as many as some chapters, but fairly close to average. Applying the concepts, the very best thing I think to study for the test, and there's 43 of those here. Your test won't be any more than 20 questions, probably fewer. So certainly more is covered here than there, and they're never the same questions, but they are dealing with the same material. So if you know these, you're going to know most of what you need to know for the test. The answers are all given. As far as I know, all the answers are right. I've never had students say, I don't think this is right. We worked through it and say, nope, you're right. They had it wrong there. A few times, most of the time. Now, in some earlier editions, yes, we did find some errors. I haven't found any in this. Okay? But maybe I haven't had the students doing it. I don't know. Let's do questions for thought. 17, that's probably right around or a bit more than average. 7 for further analysis, I think that's probably more than average. And then they have an invitation to inquiry if you want to take a look at that. The Group A and Group B parallel exercises are a lot like the examples given in the book. They're actually working out problems. Supposed to have Group A answers in the back, but I don't think they put them in the back of the book for you all. So that's going to be your and the test. I had hoped to have it done today. I ran out of time yesterday. I was so excited to get things back. I tried to get a lot of things caught up. I just couldn't get them all done. So if you don't mind pausing for just a moment, I'm going to, you're going to lose the screen, but hopefully you'll still be here. Let me go on and advance this back to where we were before so I can end the slideshow and discard that, because what I want to look for, and at some point I'll lose you on the screen. It stopped. Screen sharing has stopped, so hang on. I will be back with screen sharing in a minute, but let me exit full screen here and minimize this. And Ian is in the way, of course. You can't see that, but I'll minimize this and minimize that. And let's see if I can find, if I have that test. If so, I'll go on and put it out there. I just don't remember what format I have. I meant to do this before, but I forgot. Okay, this will be test 4. Physical Science 112, test 4. No, that's lab 4. Test 4. There it is. Okay. Now, let me see. I hesitate doing this. Y'all can't see this anyway, can you?
No, sir, not.
Okay, that's good. Oops. Nope, that's not the right test. That's a Chapter 16 test 4. That's not at all this one. That's what I was afraid of. Okay, forget that. Let's see if there's any other test 4 here. See, right there is where it should be. That just changed it to 30-30. I'm pretty sure I didn't look at that. Okay. It should be right there, and it's not there. Oh, that's physics. I'm sorry, that was my physics class. Physical science test 4 should be right there. So I'm going to have to type this from scratch. Unless I can get my wife to scan it somehow and make it faster. But I don't think that's going to happen. We don't have our scanner set up. So it's going to be Tuesday, I think, before I get the test there. If I get it done this weekend, I'll send it to you sooner. All right, sorry about that. Thought it was worth a shot, but I think I'll go on and close this out then and get back to Zoom. Come on, Zoom, come on up. Where are you, Zoom? There we go. Let's go back to the meeting and go expand my view and share the screen. And this time I'm going to I guess we're going to get going on chapter 6. Remember, we don't do chapter 5, we go straight to 6. It's 3:10, so we've got a little over half an hour. So let's get started on chapter 6, and then we'll come back and talk about the lab today. And I was really disappointed in, by the way, it's not a bad, oh, y'all don't have that generally, do you? I was going to say, not a bad idea to look at chapter 5. You may get some ideas for paper topics, so good ones there. But unless you have one of the big books, that's not going to work, okay? So, here's chapter 6. Can y'all see that? You can?
Yes.
Okay, good. All right, here we go. And this is, now in my book, this is page 140. I don't know if they did renumbering in your book. If they did, wherever chapter 5 would have started, or started in my book, that's probably what page it is. So you'll just, if I ever mention a page number here, you'll just have to take it into account. In fact, do y'all have 2 numbers on a page? One, the actual page in your book, but the other is the page in mine? I don't know if you do. Or do you have a hyphenated page, like 6-1 or 6-2? I don't know. Try to find where you are. Beginning of chapter 6. Now, the title of chapter 6 is electricity. The subject matter of chapter 6 is electricity and magnetism. So why they left off magnetism, I don't know. We're going to treat it as if it's as if these are 2 different topics, but they combine to be the same thing. Electromagnetism. That should have been the name of the chapter. But they're calling it electricity, that's fine. The course concept is, but here it is, right here in the core concept. Electric and magnetic fields interact and can produce forces. They generally do produce forces, but they certainly can. Okay? Core concept. Pretty simple, very sweet. Now, a little bit, 6.1 is going to talk about the concepts of electricity. And this goes back pretty old, the electron theory of charge. There was an ancient mystery, and one of its original names was the amber effect. Do any of you know what amber is? Some of you may think of it as a color, and that the color comes from what amber actually was. Anyone know what amber was and is? It's actually fossilized. There's a name for it. Goodness, what do you call wood that is hardened into rock that has a name? I can't think of it. But anyway, fossilized sap from something like a pine tree or some type of material. It's hardened sap. That's what amber is. And it's quite hard, okay? And it has a pretty color. And sometimes you'll find insects trapped in that fossilized, petrified, that was the name, petrified sap, okay? And you'll sometimes see mosquitoes or other things that were caught in that when it hardened, okay? And what they found, that if you took amber, a piece of amber, and rubbed it with fur or wool, either one, and snuck up behind somebody and touched them, you would shock them. And it was a great parlor game, you know, shocking people and, oh, you know, all this kind of stuff. It had to have been sort of boring back then. Okay, but anyway, that was the ancient amber effect. They knew it happened. They didn't have a clue of why it happened. Well, many people came in between, but one in particular was named J.J. Thomson, another Thomson. I don't think he was any kin to Benjamin, but J.J. Thomson identified these negatively charged subparticles that existed in atoms and molecules, and they were electrons. Now, I can't remember exactly when J.J. Thomson did this. 1856 is when he discovered it. But way before him, they knew, they were beginning to identify, and we had one of our people involved with it, Benjamin Franklin. Benjamin Franklin, I think, is the one that's attributed with calling the two charges positive and negative. I mean, he could have called them right and left or plus and minus or anything else, but he called them positive and negative, which basically is plus or minus. Okay? And I think he's the one that arbitrarily chose the negative charge to be negative, and therefore the other charge was positive. I don't know how he did it, what his process was, but that has sort of messed up electricity from my own. But we'll get there later, okay? Don't worry about that now. But J.J. Thomson finally identified what it was that held that negative charge. And these were these tiny, tiny, tiny little things that revolved around the nucleus of an atom. Now, here is the picture that, as we understand it today, probably has some few flaws in it, but it's it. Somewhere in the center of every atom is what we call a nucleus. Now, here's the incredible thing about that nucleus. That nucleus contains almost the entire mass of that atom. And it is incredibly, incredibly tiny. So it's one of the most densest things that you can imagine in nature. And surrounding that nucleus is a cloud of electrons. Now, it may not be many. This happens to be indicating this is probably beryllium here. No, this is helium. This is helium. 2 protons with 2 neutrons. That's what's tucked away in that tiny little nucleus in the center. And then you have 2 electrons flying around anywhere in these shells around it. Now, if that was truly helium, both of them would probably be in that inner circle, not in the outer circle. But it really doesn't matter. This is just sort of representing things. Okay? So most of the volume of the atom of helium, or whatever it is taken up by that electron cloud. There's really nothing there but a couple of tiny little specks of matter flying around there. But that's what creates what you might say, the outer boundary. It would sort of be like the outer boundary of Jupiter. Well, Jupiter is gas, okay? It's a gas giant. It doesn't have any solid surface at all, so the outer boundary of that would be equivalent to the space that the electron takes up here. You might say the same thing for the sun. The sun is not just a gas, it's the plasma. It has no solid or liquid or any other characteristic. It's all plasma, but yet it has a definite, it seems to have a boundary, and the boundary is where that plasma goes out to. Well, that's the boundary of the atom and molecules, is how far the electrons go out. And most of the volume is determined by how far those electrons go out. where all the mass is concentrated in that incredibly tiny little nucleus, consisting of protons and neutrons. Now, a proton is always positively charged, and a neutron is no charge, neutral charge, no charge at all. The electrons, and they're so tiny you can't even imagine them, they are negative charge. Okay? There's two of them somewhere out there. You just don't ever know where they are. You can't, they're too small to even measure. We have detected a mass, but it is incredibly, incredibly tiny. Okay, so there's the electron theory of charge. Now, so today, here's what we think. The basic unit of matter is the atom. That represents an atom of helium. Atoms are made up of electrons that fly around in a little cloud somewhere out there, and that defines the boundary of the atom. But the nuclei, made up of protons and neutrons, they make up the nucleus, and they contain almost all the mass in that tiny, tiny little center of the atom. Okay? So that's what we've got. Just to give you an idea of how tiny, each electron is about 1/10,000th the mass of a proton or a neutron. Protons and neutrons are almost the same size, almost the same mass. But the electrons, you can't detect any volume of them. You can hardly detect the mass, but what mass you see is less than 1/10,000th of the other. And yet, a neutron carries a negative charge exactly equal to the charge in that big old proton, but same size, but just opposite sign, and that big old neutron has no charge at all. So the charges don't take up any mass to speak of. Okay, so there's your today's atomic theory. That's how atoms are built. Now, what J.J. Thomson, he identified these negatively charged electrons that fly around out there. Now, you might wonder, let's go back to that amber effect. What is going on there? You rub the wool or the fur, whatever you happen to have, onto the amber. What you're doing is knocking electrons off the amber, off the wool or off the fur onto the amber. So now the amber has excess electrons. So you hold it up next to somebody and those electrons jump off and shock that person. That was the whole deal with the amber effect. Other materials like glass, you rub it with silk, and now you're rubbing the electrons off the glass onto the silk. You touch someone with the glass, you still shock them. But now you're pulling electrons away from them to try to neutralize the glass. So you get shocked either way. It doesn't matter which way the charges are flowing. The electricity is the same. That's the early concepts of electricity. Now, electric charge. I've already mentioned this. This is on page 142 is where they start talking about this. There are charges in matter. They are inseparable properties of certain particles. Electrons have a negative charge. Protons have a positive charge. You cannot pull the charge away from a proton, and you cannot pull the charge away from an electron. It can't happen. They're inseparable property of that particle. Now, what are the charge interactions? Well, it all deals with electric force, and here's the rule. Like charges always repel, unlike charges always attract. Okay? Like charges repel, unlike charges attract. Now, what if you do pull, and by the way, you never, ever change the number of protons. That would require a nuclear reaction, and we don't have those, okay? And besides, that's not what's going on in the nuclear reaction anyway. But you never change the number of protons. You're always moving electrons about. So to make something a positive charge, you take away electrons. To make it a negative charge, you add electrons. Electrons are easy to move back and forth. Protons are fixed in that nucleus and they don't move. Now, if you do move electrons, Like if you add extra electrons, you make what we call a negative ion. It's no longer an atom, it's now an ion, because an atom is, by definition, electrically neutral. So if you have a charge, it becomes an ion. If you take electrons away, you've made a positive ion. If you add electrons to it, you've made a negative ion. So it's a non-zero net charge from either the loss, which would make a positive ion, or the gain, which would make a negative ion, loss or gain of electrons. Make sense? Now here's the first example, and this one, believe me, makes perfect sense. This time, they're not saying it, but this represents lithium. Lithium has 3 protons. That's why I say it's lithium. They're not specifying that. Now, they're not showing any neutrons here. Lithium will have at least 3 neutrons. But we're not worried with the neutrons. They don't have any charge. So they're living in that nucleus with the protons. Tiny, tiny little nucleus. Okay? Much smaller than those 3 pluses there. Now this part is also true. You have an inner, what we call a shell of electrons that always contains either 1 or 2 electrons. If you're hydrogen, it's only 1. Anything else it's going to be 2. So lithium will have 2 electrons in that inner shell. And then in the outer shell, there's only 1 solitary little electron there. Because to be a neutral lithium atom, you have to have the same number of protons as electrons. So this picture back here more closely represents lithium than helium. Because helium would just have the 2 in here, nothing out there. This would have 2, lithium would have 2 in there and 1 out here. I just put the 2 out there because I had the outer shell. But this would be more to the point. And they always do this. And we'll get to that later in next chapter, if we get there. I don't know if we'll make it or not. Okay. That's a neutral atom of lithium. You don't have to name it lithium, just a neutral atom. That's all the book does. Now, this next thing they do makes sense. Because that 1 electron was out there all by itself, it's farther removed from that positive nucleus, so it's not held as tightly as these 2 are. So therefore, if something comes along and yanks it away, it's going to leave. And if it does leave, now you have 3 pluses and 2 minuses. That's a net plus. So that would be lithium with a +1 charge. That would be a lithium ion. That makes sense. That does happen in nature. Okay? That does happen. That 1 little electron out there gets yanked away by something else, and it makes a positively charged lithium ion. This next one, in theory, kind of makes sense, but in reality never happens. That's that lithium atom picking up an extra electron. That's not going to happen. Okay? And there's a reason. We'll get to that if we get to chapter 8. We'll get to that. But this would then be a negative ion. Okay? Because you have more electrons out here than you have protons in there, so that would be a negative charge. And if this were really true, you would express it Li with a minus. It doesn't happen. Lithium never makes a negative ion. It does make a positive ion, but never a negative. Now, if they had shown fluorine or chlorine or something like that, yeah, that happens. They pick up electrons. Lithium only loses if it loses. Okay? But they're just trying to illustrate a point. That would be a negative ion. Okay. Now, that was the figure 6.3. Okay. Now, back to our amber effect. That was an example of static electricity. You rub the amber with the wool or with the fur, and you build up excess electron charges on the amber. But they just sit there until you touch somebody and they jump off. That's called static electricity, and that basically means stationary, fixed, not moving. The electric charges get in place and they stay in place. So the electrostatic charge is a stationary charge confined to that object, whether it be amber, glass, whatever it happens to be. What are those charging mechanisms? Well, one would be friction. Rubbing the amber with the wool or with the fur, that is going to knock electrons. The friction that you do knocks electrons off the wool, off the fur, onto the amber. Another way you can do it is contact with a charged object. You take that charged piece of amber and hold it near, say, a little scrap of paper, and it'll pick up that paper, and now that little piece of paper becomes charged because part of that excess charge moved to the paper. So contact with another charged object that will be a charging mechanism too. But then a third one, polarization. Now this is not changing the total charge, it's changing the location of the charge. And I think they have an example of that here. In the first place, here's friction. I know she got upset. She probably has just washed her hair not long ago, completely dried it, so it's completely dry and clean, and she starts combing it with, say, a rubber brush, okay, rubberized brush or comb. And as she does that, the comb starts taking electrons off the hair and moving them to the comb. So now the comb gets negatively charged, leaving her hair positively charged. But because different hairs are all positively charged, now they are separating from each other. And now her hair looks worse than it did before she combed it, because they're trying to repel each other. Because like charges repel, unlike charges attract. Okay? So that's an example of friction as a charge mechanism. Now, they don't show one with a charged object. If you did, let's go back here, and you touch that comb, which is negatively charged, to, say, some other rubber object, and then pulled it off, both of them would be charged negatively, but less so than the original comb was. That would be contact with a charged object. They don't show that. They don't illustrate it. But they do illustrate the third one. This is polarization. Now, these are not handy-dandy little pieces of paper. This is usually scrap paper torn up into irregular shapes, very light, and you have that charged comb with excess negative charges. You hold it down. Don't even touch the piece of paper. Hold it close to the piece of paper. When you do that, the positive charges in the paper move toward the negative charges in the comb, because unlike charges attract each other, but that leaves the negative charges in the paper, which are trying to move away from the comb, because like charges repel each other, they move down to the lower part of that paper. And even if you could get that comb, especially if this was a smaller little scrap piece of paper, you may be able to lift that piece of paper off the table. But then that would lift the one below it. And the one below it, you'd have a chain going until it got too heavy and then they fall. But the reason is you are polarizing those pieces of paper, redistributing, realigning the charge, making the positives go up here, the negatives there. So then the next piece of paper, the positives go here, the negatives there, and they make a chain reaction, you might say, a chain effect. That's polarization. All right. Make sense? All right. And what they were showing here, the paper was originally neutral. They're way too organized here, but they're randomly distributed charges. You get down here, and now the positive charges move here, the negative charges there, and they're no longer randomly distributed. That's the point. All right, let's move on to, and by the way, there's a concept applied here, static charge, and you certainly might be interested to do that one. That's up to you. But at the bottom of the right-hand column of page 143, electrical conductors and insulators, that's where we're moving to now. Well, electrical conductors are materials where the electrons are free to move throughout the material. any charge that you put on that material, it spreads it out over the entire piece of material. Okay? Examples are metals. And we talked about this in the last chapter in the heat and temperature. Good electrical conductors are usually also good heat conductors. Now, they may not follow the same order, but they usually are. Metals are good conductors of heat. Remember those aluminum bleachers? And metals are good conductors generally of electricity as well. The reason for that, metals have what they call those free electrons. Now, I'm going to do this. I've learned you can do it. I didn't think about doing it before. And it may not be in the back of your book, but somewhere in your book, can y'all see the periodic table there? Am I too close, too far, too right, too left, too high, too low? What is it? Can you see that? You can see it?
No.
You can't. Trying to get near my, where is my, is that my, whatever we call it, camera right there that I'm putting my thumb over? Can you see me?
Yes.
Okay. Did I put my thumb over the camera?
Yes.
Okay. So I'm trying to get this so you can see it. Can you see that? Periodic table. Yes or no?
This is not clear.
Say again?
You can see it.
You can. Okay.
But I won't be able to read it.
Okay, right. What I want to point it out, hydrogen's up here at the top. Helium's over here. You're just counting 1, 2. Over here we have what they call the soft metals. Okay? Not really metals as we usually think of them, but lithium's right there. Okay? But most of your metals are in this portion down here. Now, over here and over here, the electrons are fixed pretty much in place. But in this middle group, and that's where you see most of the metals, I'll read some of them to you. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Next row, molybdenum. A lot of these I'm not familiar with. Silver, cadmium. Next row down, gold, platinum, iridium, osmium, and mercury. Those are your metals. They're in the middle there. And the reason I pointed that out to you, I've lost my place in the book, so let me go back and find my place in the book. Okay. Should have had a piece of paper marking the place, but I didn't. Okay. I'll get there one of these days. This is a long chapter, by the way. Okay. Yeah, here we are. Okay. Those metals in the middle part of the table, there the electrons don't get fixed in place. They kind of float. Okay? They have the right number of electrons and everything, but they're not really named. This electron belongs to that place. Okay? So therefore, when you have a whole bunch of them, they're free to move wherever they want to. That's why we call them free electrons. That's what conducts the heat. That's what conducts electricity. Now, graphite is a form of carbon. Does anyone have any graphite near them? Anyone have a pencil lead? A pencil lead, the black stuff that comes off on your hand, that's graphite. Now, what makes that graphite harder is they mix it with kaolinite, which is a clay. And that gives you hard leads and softer leads, depending on how much kaolinite's in there. What's that? That's graphite. You can think of it sort of as the soot in your fireplace, okay? That's carbon. The black deposit that gets when you burn a lantern, that's carbon. That's graphite. It's real slick. It's a two-dimensional crystal structure, really slick. It gains and loses electrons really, really easily. Okay? It's pure carbon. Now your electrical insulators, now your electrons are pretty much every one fixed in some particular place. The electron motions are very restricted. You don't have those free electrons that can roam the neighborhood wherever they want to. They have to be. Those parents make them stay right where they, no, I'm just kidding. Okay, those are electrical insulators. You don't have free electrons. The added charge tends to stay right where you put it on the object, on the surface. It doesn't move. It's not distributed anywhere. It sits right there. Examples of good electrical insulators: glass, wood, and guess what? Diamond. Guess what diamond's made of? Pure carbon. Diamond basically is graphite that's been heated, pressurized, and everything until you changed its entire molecular structure. Now you have a three-dimensional structure that not any electrons are allowed to go anywhere. They're all fixed in place. Graphite, they're free to move. So that's the difference. Same, exactly the same element, but different crystal structure. Okay. And then you have another called semiconductors. They sometimes conduct and sometimes insulate, depending on your circumstances. And one of the big uses for those are computer chips, but also solar cells. They're anything that takes the advantage of the freedom of movement in one direction or in one condition, but the lack of movement when the condition changes. That's a semiconductor. And they don't give any better description than that. They're just really important. And remember, one of these, and by the way, if I can get my thing back up here, I'll try to hold my fingers in place this time. I tried it before, but let go. Okay. Notice most of the blue in this periodic table, those are mostly metals. Mostly over here, and those are good conductors, by the way, generally. The ones over here, those are non-conductors. The green up there, that's your semiconductors, or at least materials that tend to become semiconductors. They conduct to some extent, but not to others. Okay, just to give you an outline there. Okay. There is a table in the book. There are many tables in the book, but in table 6.1, they list some of the conductors. See if this list sounds familiar. The best conductor, this is electrical conductor, silver. Next best, copper. Then on down the line, gold. On down the line, aluminum. Then your graphite carbon. Then tungsten, then iron, then lead, then nichrome. Nichrome is a alloy of nickel and chromium. I don't know what the ratio is, but it is. That basically, I think, do any of you have electric ranges or ovens in your house? Anybody? Or you all use gas for everything? Yeah, you do. That material that's either the plate of on your range or that strip that runs around inside your oven, that when you turn it on, it gets red, it gets really hot. I'm pretty sure that's nichrome, okay, or something like nichrome. Not a great conductor, and that's why it gets really hot. But it conducts enough so it does conduct electricity. Your insulators, on the other hand, this is probably from best to worst here: rubber, glass, carbon that's diamond in form, plastics, wood. Okay? Those are generally insulators. Now, the reason I said that should look familiar, very similar to the table we had back in chapter 4 of your heat conductors. The very best heat conductor was silver. Next to that, copper. I don't know if they listed gold, but aluminum was in there, and on down the line. They didn't list them all, but almost exactly the same order, because it's exactly the same physical, microscopic reason, free electrons. Okay. Now, let's move to electric charges. They're going to talk about measuring charges here. Okay? The unit of charge, itchy nose, we must be going to have company. Unit of charge is a coulomb. Now, actually, that's not the smallest unit of charge. That's the one we use to reference. Oh, and by the way, it's a capital C because it's named after, I think his name was Charles Coulomb, a French physicist. And I think he lived about the same time that Benjamin Franklin did. And I think Louis Ampere lived about the same time. And guess what? Benjamin Franklin was at one time our ambassador to France. And yes. Is it? It's 3:44 on my clock. Okay, no. Let me get this slide done, and then we'll be finishing up. The smallest unit of charge is that electron charge. You can't get a smaller piece of charge than that. But you talk about small, that is so incredibly small, it's hard to believe. So, what a coulomb is, something we can measure with instruments, that is equivalent to the charge of 6.24 times 10 to the 18 electrons. That would be 6,240, 000, 000, 000, 000. You'd have 6 groups of those 3 zeros, with the 240 being the 6-1. That would be how many electrons. I don't even know the prefix that you would go with that. Quazillions, of electrons. The coulomb is the metric unit of charge. But not only that, it's also the English or U.S. equivalent measure of charge. Everybody uses the same thing for electrical. Why? Because the British and the English and the French didn't have separate units back then. This all came about after they started working together a little bit more. The electron charge is the fundamental charge. You can't get any smaller than that, smallest charge seen in nature. And the quantity of the charge and the number of electrons, they're related. And this is the formula. Q, remember in the last chapter, Q was energy unit. Now it represents the amount of charge. The amount of charge, this would be typically in coulombs, would be N times the number of electrons. If that was 1 coulomb, this N would be 6.24 times 10 to the 18 electrons, where E is the electron charge. So that's the formula that goes from electron charge, which is the smallest unit in nature, to coulomb charge, which is what we usually use. And here is the equivalence. 1 electron charge is the charge of 1 coulomb divided by per N. If you divide both sides by N, okay, the N's go out, and the electron charge would be Q over N, and that would be 1 coulomb divided by 6.24 times 10 to the 18 electrons, and that comes out 1.60 times 10 to the minus 19 coulombs per electron. That would be 0.0000000000000, a total of 18 zeros before you get to 160. That's a small amount of coulombs per electron. Now, I asked them to put, they may not have put it in the front of the book, but somewhere in your book, the physical constants, okay? And if you look under there, you'll see fundamental charge, and you'll see that number right there, 1.60 times 10 to the minus 19 coulombs. It's the smallest unit of charge you can find in nature. Okay. Now, we'll begin next time with electrostatic forces. Okay? This slide here. So I will wipe out this other mark that I have on that page and make sure I don't have any others. And that's where we'll begin next time. And now, folks, kind of the bad news for you. I tried last night to come up with a lab that we could do today that dealt with heat, because of all the mess ups with technology, computer breaking down, internet going down, all like that. We couldn't do labs any earlier. So finally, when I was able to access, and I don't know if you realize this, when we lost the internet and were running off Karen's hotspot, I couldn't open Blackboard because Blackboard drew more oomph than the hotspot was able to provide. So I couldn't open Blackboard, so I couldn't get to the thing. So what I'm going to do here, I'm going to share a different slide here, and hopefully we can go here. That didn't work, did it? Let me try again. New share. This is what I'm trying to get to. It's not going there. Sorry about that. So what I'm going to have to do is get out and then bring you back in. So hold on and let me start minimizing some things here. Let me get Tarsha out of the way. She's blocking my view here. Okay. Well, everything's hung up now. Tarsha, it's your fault. Okay. There we go. I had to. Okay. I had. See, your name is showing up, and it was blocking where I could see what I was doing. All right, now it's blocking it again. Look at you, always in the way. Okay, there we go. I'm going to close this, and I want to minimize that because I don't want to lose it. Now I'm going to, you probably, at some point, well, can you see what I've got here? My screen? Say again?
Timer.
You can only see the timer?
Yes.
Okay. Can you see the Windows symbol here in the middle? This is my, well, never mind. I'm going, okay. Now, going back to, come on. Trying to get back to Zoom. Right now it's not going there. I don't know why. Okay. Oh, here we go. Goodness, this is not coming up. There we go. Back again. Recorder is recording. That's what I want it to do. So keep recording. Okay, new share. Here it is. Maybe that was there all along. I don't know. Let's see if it was. Okay. I've gotten back to my simulation. Y'all all know how to get here, right? Can you see this? Can you see the simulations? FET, interactive simulation? Yeah, okay. So let's go down to physics. Now this, sadly, I don't have a lab prepared for you, and I was just really shocked to see how few things they had here that had anything to do with heat. If you see any title that looks like it deals with heat, stop me. But I've looked and looked and looked, and I don't see anything. There's plenty of electrical stuff, so we got plenty of that coming up. But I don't know how many they're any good, but we're going to have them. But nothing here is really dealing with heat. Electric. There's the energy forms. Now this had some heat in it. So let's go back to this one. This is one we looked at before. And remember, I had been doing download and telling you to download. I found out just hitting on this triangle here actually works faster. Takes you right there. If that doesn't work, go back to download. Okay? Now, it takes a few minutes. If you're downloading, it takes a few minutes. If you hit this key, it takes a few minutes. But this gets you right there without having to open again. Now here is the intro form here. We didn't do this before. Okay? Now, I tried messing around with this. There, Ian's in the way. Now you people just get in the way all the time, don't you?
How rude,
Okay.
Fowler.
Okay. Well, I can't get rid of you now. Okay, there we go. All right. I want to turn on the energy symbols showing how much energy is in this. I don't think I want to link the heaters yet. We may later. Now here is our thermometer, and we can use that when we want to. So let's move the water over here to the burner, and let's take a thermometer down from here and put it against the water here so we can measure the temperature of the water. All right, now what we're going to do is heat this. Now what I want you to notice is what are happening with your energy units, and at the same time note what's happening to the thermometer. I found this pretty lame, but let's see what we can get out of it. You bring up the heat, and what do you notice? There goes one. Yeah, you get these heat energy units going up into the water. And what's happening to the temperature?
It's rising.
It's increasing. And at somewhere here, it stops. And notice what's happening here. Energy's going into the water, but it's also going out into the room. And what do you see here? Can you tell that? Steam. What you've now done is reach what point would you call this temperature?
The boiling point.
The boiling point. So that would be a good thing to do. Here are some things you can answer. When you turn up the heat, energy units start going from the water, from the heat source to the water, but then, now, it takes a while for the energy to come down. Okay, I accidentally increased that. Oh, I've got to get my finger off of that. If I take my finger off that, the temperature is coming down. Now, when it reached the boiling point, did the temperature go up any higher? Take a look at it. There the temperature is, I have to keep my, okay. Temperature goes up to this line here, and I'm adding heat. I'm adding heat big time down here. But is the temperature increasing?
No, it remains the same.
No. So what's happening here? If it's not changing temperature, what's happening here? Change of phase from water to steam. You see the steam here? And all the heat coming in here is then leaving here by changing the phase of the water from liquid to gas. Okay? Now, what I want to do is go back to the beginning. I don't know if I can. Let's chill that water down. What happens to the thermometer here? Well, I don't think it's working, is it? Oh, yes it is. There's still steam coming out. As long as the steam's coming out, it's still at the boiling point. But once that steam quits, see, no more energy is leaving. That's still not moving. There's got to be some way to get it go back. Maybe this will. Nope. Okay. Well, tell you what we'll do. Let's try this. Okay, it seems like we're frozen in place here. But here's what I want you to write down for the lab. When you started heating the water and the temperature was rising, what formula represented what was going on in here? If you have a change of temperature, what kind of heat were you dealing with? If it was just heating the water, That dealt with, anytime you had a change of temperature, you're dealing with specific heat. Remember?
Yes, sir.
Okay. What formula represented the heat loss or heat gain with specific heat? I don't know if this is going to work here. No, it's not. I thought maybe I could write on it. I can't. This experiment doesn't allow that. Okay. That was Q equal, anyone remember?
Is it J time?
Okay. If any of you have your books open still, go back to chapter 4. We were just in chapter 6. Go back to 4. And it's on page, where is it? I know it was on a slide. I know it had to show up in the book somewhere here, but I don't see it. Okay. This is put together really poorly. We did several problems with it. So maybe one of the examples will show it. Yeah, it's had to be in here. Oh, I remember. Okay. The specific heat, it was back several pages. Remember I said at the time, I don't know why they break them up like this. Go back to page 97. Equation 4.4. It's also in the summary if you have it there. Q is equal to?
MC.
Oh, wait a minute. I found how I can get it to go back. No? Ah, there we go. Now we've gone back. Okay. That cleared everything. So let me do this again. Put the water over the pot. Come on, get over there. Don't break the beaker. Okay. Now, get your thermometer in place. One thing I don't like about this thermometer, it only goes up. It won't go down. So we can only deal with liquid water and steam. Right now it's liquid water. We don't know what temperature that is, but we know it's not as hot as it could go. So what happens when we add the heat? This is your first question here. What happens when you add heat? You'll see the energy units increasing, going from the fire to that, and what happens to the thermometer?
The temperature increases.
Temperature increases, okay? That is, in that range, what you're doing, here's the first question. What are you doing then? You're heating the water, resulting in a temperature change. Okay? What formula reflects that amount of heat that's happening? It relates the temperature change to heat. That's the one on page 97. Has anyone found it? Q is equal to, we used it several times last time. Remember, I was writing it down and showing it in the camera. Q is equal to MC delta T. M is the mass of the water. They don't give us that here. C is specific heat of the water. That one you should remember. 1 calorie per gram degree Celsius. Water is used for our standard in so many things. And then the delta T was a change of temperature. We started down here somewhere. We went up to that line. It wouldn't go any higher. Okay? So that's your change of temperature. That's governed by that equation, so specific heat equation. Okay? Q is equal to MC delta T. Now, turn up the heat some more. And notice the temperature is rising. It keeps rising. It keeps rising. But then it stops right here, and what do you see coming out here? Can you see the steam?
Yes.
So what you're doing now, you're no longer heating the water. It got up to what temperature you think this would be? What temperature do you think that would be?
The boiling point.
The boiling point. Perfect. That's one of your answers, boiling point. And what would that be on your two temperature scales? On the Celsius scale, what's your boiling point? 100 degrees Celsius. And what would it be on the Fahrenheit scale? Oh, you don't know your Fahrenheit, huh? 212 degrees Fahrenheit. Okay? Now, notice the temperature is now decreasing. We took the heat away, so the temperature is decreasing. Okay. When the temperature is decreasing, you still have a change of temperature. It's still that same formula. Q is equal to MC delta T. The Q now are these occasionally energy units that are going into the air. You're losing, there goes one. You're losing the heat, and you're losing it by that formula. Q is equal to MC delta T. Whatever it was from this point to that point, there's your delta T. The M and the C are basically the same. Okay? Now, let's go back to the boiling condition. Okay? The temperature is I have to keep my finger on the thing here. Okay? The temperature is increasing until it reaches here, and then you start seeing the steam. That means you're boiling the water. And now you're at the boiling point. You do not change temperature when you're changing, what's that word? From liquid to solid to gas. Changing phase, exactly. When you have a change of phase, you do not have a temperature change. What formula? Now write that down. What formula are you using when you're doing that? Changing from liquid to gas. That's on page 102. There are actually two formulas there. One small difference, and it makes a difference here. What would that be? Equation 4.6. Q is equal to, anybody got it? M times LV. What is that LV? L stands for latent. The latent heat, not specific heat, but the latent heat of vaporization, because you're evaporating that water away, right? So the sub V means vaporization, changing from a liquid to a vapor, to a gas. It goes at a fixed temperature because you're doing a change of phase. Okay? Now, we can't show freezing. It just doesn't allow, the thermometer doesn't go any lower than what it does there, so we can't show it getting that much colder. Okay? It will slowly drop, and we see it dropping now, but that's following QM delta T. QMC delta T. Q is equal to MC delta T. Okay. And that's about all I can get out of this. It's not very much. When we had the systems here, remember we did this one last time, and I couldn't think of much you could do here, except when we had the pot here, and now we could increase the temperature of the pot, but you don't see any thermometer. You don't see, the only thermometer is over here, but now the energy units are heating up the thing, but you see you ultimately change the water in the pot to steam. It's the same thing as before, but there's not much you can do with that. Ultimately you get this up to the boiling point and it's steaming too. But that's a different issue. So I don't know if you can think of anything to do with that. All right, so let's end that and take it back to where it was, and we'll go back home. Okay, that's all I could get out of this one. So let's close this one out. I think, okay, we must have lost somebody. Let's go back to laboratory simulations. I didn't mean to get that far out. Can y'all still see everything here?
Yes.
Okay. Simulations, physics. Okay. This time, that was the energy transformation, forms and changes. Everything else is electrical there. There's Energy Skate Park that had nothing to do with heat that I remember. Okay, this is again electrical or forces in motion that we already covered. Fluid pressures and flow, we're not doing that. Forces, Fourier, friction. I looked and looked and looked. There's one more in here. There's a lot of electrical and quite a bit of motion. Magnets and electromagnets. There's our moving man we did before. Come on, I remember there was one more in here somewhere. If y'all see anything that looks like heat, let me know. I found one more, I just don't remember. Ah, here it was. I think this is it. There's actually two here. And frankly, I found these to be awfully lame too. So we'll do this one first. Well, I thought we'd do that one first. Here we go. These things take a while to load, so don't get... this is called states of matter, which we should be calling phases of matter. Now, I looked at this one, and here's the only thing I can figure out here. This is supposed to be solid neon. And that solid neon, they say, is at 14 K. Okay? What would that be in Celsius? How do you go from K to Celsius? Here, go back a few pages to your temperature part of the chapter, and there you have it on page 93, equation 4.3. If you know the Kelvin temperature, 14, how do you get Celsius?
You have to convert it.
And how do you do that? That's what I'm asking. Have you got your book open? Page 93, equation 4.3. What you do is subtract 273 degrees from your K. That's going to give you a very small number. It's going to be a negative number. Do the math. Someone do that. 14 minus 273. It's going to give you a negative number. A very negative number. Anyone do it?
259.
Second?
Is it 259?
Negative 259? Let's see. Yes, look at that. Negative 259 degrees Celsius. Notice with K, you do not put a degree symbol. With Celsius, you do. Okay? Now, that was a question. Be sure you write that down on your lab. 14 degree K is equal to negative 259. Show how you got it. Subtract 273 from the K, and you get degrees Celsius. Yes. Say that again.
You sent the lab questions already?
Say that one more time.
Did you send the lab
No.
questions already?
I couldn't find enough to do it, and by the time I finally found all these, it was 9:49, and I still couldn't type them up. That's why I say write them down. That's what I'm trying to say. Just like we did those first two, we're just writing them down. This is the lab today. Okay? What's that?
Will this video be uploaded in YouTube?
Well, yeah. You mean what we're doing here? Yeah. You see the screencast-o-matic is still ticking along, so you'll be able to see this. Yes. Now, when it'll get there, I don't know. Maybe not later tonight. It may be tomorrow sometime, but it will be on YouTube. Okay? And it will be chapter, it'll say Physical Science 111. And let's see, today we started in 4.4 through, well, 4.4 through what was the last section here? 4.4 through 4.5, and then 6.1, and we may still be in 6.1. Let me see. Yeah, 6.1. 4.4 to 4.5. What did I say? 4.4 to 4.5 and 6.1. That will be the title, and then it'll say lab, whatever today's lab is. I don't remember which number it is. Y'all remember? 7? Is it lab 7? Lab 7. So that's what it'll say on the thing. Okay? So here's the question to answer. It's solid neon. Now, neon is an inert gas. It's really cold to get it into a solid form. That's what you get. Now, and see, gases all sort of stay together in a group. You see, they're always moving. Molecules are always moving. They never stop. They used to think 0 Kelvin was where all molecular motion stopped. We don't think that anymore. We know molecules always move. Now, what we're going to do here is add just a little bit of heat. And what happens to the molecules? They move faster. In fact, now they're leveling out. That means they're becoming a liquid. Now, it got them too hot, and now they're going to a gas. So you didn't see the liquid phase very long, but it didn't have to get very hot, like 30 degrees Kelvin. What would that be Celsius? How do you go from Kelvin to Celsius?
Give me a moment.
Say again?
Just a moment.
Okay.
So is that negative 243?
Yeah, you subtract 273 from 30, and what do you get?
Negative 243.
Say that again.
You said you subtract the.
You subtract the 273 from 30. 30 minus 273.
It's 243.
243, negative 243, you're absolutely right. Okay? And at this stage, most of the neon here is in liquid phase because it keeps the shape, but some of it is escaped and become gases. The higher energy molecules escape, the lower energy stay down here as liquid. We talked about that in today's chapter 2. Okay? I'm tired of neon. Are you? Let's go to water. Okay. Now, I don't know. I want to cool that water down. They look like they're shivering, don't they? No, that's not what's happening. Now, I can't tell for sure. It should be, if it's at 257 K, oh, I know, I'll release that. What would that be on oh, I'm getting really cold. That water is at 26 K. What is the state of that water, or phase of that water? They're all in a crystal structure here. They're still moving. They always move. But that is a solid phase. You know it is. Look how cold that is. Okay? Now, I'm going to try to raise this to see if we can make it become a liquid. At a liquid phase, the molecules aren't held in place. They'll start moving over and over and around each other. So let's see if we can tell when that happens. When you add some heat, they vibrate more quickly, so you can write that down. Okay? Add more heat, they vibrate more quickly. Notice the temperature is going up, but they're still in their solid phase. They're still in their solid phase. They're still in the solid phase. They are beginning to lose a little bit of their solid phase. And they become a liquid. Now they're moving past each other. That's right at what temperature? What's the temperature up here?
273.
273. What is that in the Celsius scale? What's 273 in the Celsius scale? 0 degrees Celsius, exactly. And what does that mean? Now it's become a liquid. Okay? That happens. That's where your change of phase occurs. And you see they're moving around. This is more liquid here. Okay? See what? Okay? And now they put it, when I put the liquid on, they moved it to 286. That's all liquid now. You're already above the freezing point or the melting point. You're at 286. What's 286 Kelvin? What would be that temperature Kelvin? No, I'm sorry. 286 Kelvin would be what temperature Celsius?
13.
15 you said?
13.
13, you're absolutely right. I can't hear well. Okay? So, that's your liquid water. And you see, they take the shape of the container, they're moving past each other. So let's add a little heat to that and see what happens as they heat up. Number one, you see they're moving more quickly. Some of them are really getting bounced around a lot. Some have a lot more energy than others. And the temperature keeps rising, and it keeps rising, and it keeps rising, and a few of them begin to, the more energetic ones, escape. There goes one. Okay? Now, we start seeing that happening about 269. All of them aren't doing that, but a few of them are. What's that in Celsius? 269K. 369K. What's that in Kelvin? I mean, what's that in Celsius? I can't talk.
96.
96. That's awfully close to the boiling point. And look at that. More and more of them are moving. Let's get up to, what temperature are we now? 102 Celsius. You're absolutely right. And there we're beginning to see it's boiling. More of these are coming out into and becoming water vapor. So let's show the gas here. And there it is. All of them are gases now. What temperature is that?
Just a moment.
No, it's 430 K. Answer that, and then calculate and see what it is Celsius.
157.
Okay, let's see. Yeah, 156, they said, yeah. I don't know why they say 156. It would be 157, okay. They can't subtract, okay. We didn't do the solid. Let's go down here and see the water is a solid. That's where we had it before. And what temperature was that at? 146 K, that's a good answer. What temperature would that be? Celsius.
127.
Negative, right?
Yes.
Negative 127 Celsius, because that's a solid. Okay. It's pretty lame. You can play around with others if you want to. Now this one, I tried to do some things with that. It doesn't look much different from the other. For some reason, she has her finger on this one, or he does, whoever it is, and whatever. It starts back with neon, solid neon. That's unbelievable. That would be solid. It does show something over here that we haven't done. If you add pressure to it, you can change the boiling point and the freezing point. You can change the others, and you can actually get a place where the solid, liquid, and gas all come together, and that is called the triple point. And that would be for any material. This happens to be neon. But pressure is involved with that. We don't usually do that. So I can't really think of much else to do with this one. And then interaction, I really couldn't tell. Well, this is drawing graphs, and it's dealing with noble gases, so I think that's beyond what we're doing. Okay? So we're losing people like flies, aren't we? Okay. Let's go to the other. Yuck. I want to just go out, but maybe I should go home. That probably would have gotten me there. Okay. Go back to simulations in physics, and we'll go back down there where we were. I don't think these are much better. States of matter, basics. I think this is the last one that I saw that had any likelihood of, yeah. I think this is just like the other one. Didn't really make a lot of, in fact, I mean, it was so similar to the other one, I couldn't tell much difference, if I'm remembering right. Yeah, there were the states. That was exactly what we had before. And then we did phases. And that just added the pressure to it. They didn't have the phase diagram. I guess you could have added that. So, I don't know. Get all that you can out of that. Write me up what you can. You saw where we went. Energy forms and changes or something like that. And then the states of matter. And I found the other one just as good or better than this one. So just show me you've done something and turn it in. Okay? You can take pictures of what you're doing, showing the thermometer. I don't do, just do something to show me you played with it some and turn it in. You'll get your credit. Okay? It's pretty weak. I'm sorry about that, but this is, I was just shocked to see so little here. If I would have had more time, but I've been fighting with the, with not having internet, with my computer being out, with all these things that I couldn't do. And then when finally I got it, I mean, that was less than right at a day ago, you know, is when we finally got things back going again. So I just didn't have time last night to do it. So with electricity, if you notice that list, there are tons of things with electricity. Okay, no, home didn't take us any further. So we'll have plenty to do with the electricity chapter. And then if we get to chemistry, there's a few things there. But actually, I have a lab that I'll send to you that will cover the chemistry. And there's only one lab there, and it's all a paper lab, so we'll go to that. Any questions? You feel okay with it?
Yes.
Okay. Well, then we will, I guess, sadly have to go. And I hope you all have a good, safe weekend. And if I can get you that test sooner, I'll get it before next week. But I've got to type it up from scratch. So it shouldn't take so awfully long. But usually when the weekend gets here, well, tomorrow morning, I'm going to be advising students. I don't know how many I've got, but last Friday morning, I had 6 of my 8 half-hour segments were filled up, and then I had a department meeting. So that ate up my entire into mid-afternoon, and then the boss had plenty of things for us to do that last weekend. So I can't promise I'll get much done this weekend on it, but hopefully next week I'll have more time, and in the evenings I'll have more time to get stuff done. So y'all take care, have a good weekend, and we will see you. And this that we did today was Lab 7. And anyone that wasn't here, if you run into them or whatever, I mean, not physically, but electronically or remotely or virtually run into them, let them know that the lab is out here. You'll just have to follow what's being said, write up something, and get it to me. Okay? All right. Have a good weekend. All right. I'm going to stop the share, and I'm going to end the meeting. No more questions? Any other questions? Okay. Y'all look pretty fired up. Okay. I'll try to end the meeting here, and we'll end it for everybody. Never did get who Galaxy was. That was a new one.